Hi everyone, Tina here, and today I'd like to talk about forces and motion. We'll be using F equals ma, and I'll talk about resolving forces into components, inclined planes, friction, and static rigid bodies. You'll usually learn about these topics during year 2 of your A-level course. I have made another video on forces in year 1, so I'd recommend you watch that video first if you haven't already. Go through some key ideas first, and then we'll look at some examples. So some key ideas for year 2 are here. First of all, when you're resolving forces at an angle, you'll need to split the force into its components. So for example here, this component of the force F will be F cos theta. And this is because this is the component that is touching the angle theta. In other words, it's adjacent to the angle. And that word adjacent should make you think of CAH or Ca in SOHCAHTOA. Therefore, we use cos. There are other ways of working that out, but I think if you can remember the trick, that's the quickest way to do it. If that component is cos, then the other component will be F sine theta. Again, you can do that with a right angle triangle and using trigonometry, but it's quicker just to remember the trick. Moving on to friction, FR here stands for friction. And generally, FR is always less than or equal to mu R, where mu is the coefficient of friction, and R is your normal reaction force. Because friction is always less than or equal to mu R, we could consider the maximum friction as being equal to mu R. And most of the time, we'll use this in calculations. I have a note here about moments. Sometimes you'll need to use moments with questions that involve forces as well. And the moment about a point is equal to the force times the perpendicular distance. If the system is in equilibrium, then the clockwise moments will be equal to the anti-clockwise moments. Last note on this page says that limiting equilibrium is when a body is on the point of moving. So worth bearing that in mind. Let's take a look at some examples. Example 1. A block of weight 10 newtons is at rest on a rough plane, inclined at an angle of 26 degrees to the horizontal. The block is on the point of sliding down the plane. Find the coefficient of friction between the block and the floor. Now, because it's on the point of sliding down the plane, that means the system is in limiting equilibrium, so on the point of moving. When we have limiting equilibrium, then friction is at its maximum. So we can say friction is going to be equal to mu R in this case. First thing you want to do is label your diagram with the forces. So we've got the block of weight 10 newtons, so let's put the weight on, coming straight down. Now when you've got an inclined plane, you're going to want to resolve parallel and perpendicular to the plane. So at this point, I would actually resolve that weight force into its components. So going that way and that way. This angle here is also going to be 26 degrees. And therefore this component is going to be 10 cos 26, and this component is going to be 10 sine 26. So the 10 cos 26 component is the one touching the 26-degree angle. Other forces we have will be the normal reaction force, acting in this direction. And then it says it's on the point of sliding down the plane. So I'm going to put acceleration going down, even though it's not accelerating at this point, just so I can see then that the friction would be acting in the opposite direction. So FR for friction going up the plane. Now we can resolve our forces. So first of all, we're going to resolve parallel to the plane, so in this direction. And if we think about Newton's second law of motion here, so F net equals ma, the net force going down the plane is going to be 10 sine 26 minus the frictional force. And that's going to be equal to 0 in this case because the particle is not moving, so acceleration is 0. That means we can rearrange this now to get 10 sine 26 is equal to friction, and we know friction is going to be equal to mu R. This is all we can do at this point. So now we're going to resolve perpendicular to the plane, so in this direction. Now, because the acceleration is 0 in this direction, we can use the trick that will say the forces up will equal the forces down. So in this case, R is going to be equal to 10 cos 26. That's useful because now we can take that R value and sub it into here. So we're going to get 10 sine 26 is equal to mu times 10 cos 26. And then we can rearrange for mu. So mu is going to be 10 sine 26 over 10 cos 26. And that turns out to be 0.48773, etc. So roughly 0.49 to two significant figures. And we're finished because we found mu, and that is the coefficient of friction. Example 2. A block of mass 2 kilograms is at rest on a rough plane inclined at an angle of theta to the horizontal, where tan theta equals 0.75. The block is released from rest. The coefficient of friction between the block and the floor is 0.2. Find the acceleration of the block. So first thing I'm noticing here is that we're not actually given the value of theta, we're given that tan theta equals 0.75. When this happens, you're going to want to work out the exact values of sine theta and cos theta from this. So if tan theta is 0.75, another way of saying that is 3/4 or 3/4, you then need to draw yourself a small right-angled triangle with theta here. That would mean this would be the opposite, this would be the adjacent, and this would be the hypotenuse. We know from general trigonometry or SOHCAHTOA that tan is equal to opposite over adjacent. So that means the opposite in this case is 3 and the adjacent is 4. Using Pythagoras, that means the hypotenuse is going to be 5. And from here, we can derive the values of sine theta and cos theta. So sine theta, opposite over hypotenuse, so 3/5. Cos theta, adjacent over hypotenuse, so 4/5. Those will likely come in handy later. We're also told that the coefficient of friction is 0.2 and the particle is accelerating or moving. So that means friction will be at its maximum, mu r, and in this case, that's going to be 0.2 r. Now I would label the diagram. So because the block is released from rest and it's on an inclined plane, it's going to travel downwards, acceleration this way. This time it's a mass of 2 kilograms, so the weight would be 2g. Again, I would resolve this into its components. So this is theta, means this will be 2g cos theta, and this will be 2g sine theta. We've got our normal reaction force, and we've got friction going up the plane. Friction always opposing the direction of acceleration. Once again, because it's an inclined plane, we want to resolve parallel and perpendicular to the plane. So we can start with parallel. You can start with either, but I usually start with parallel. And parallel to the plane, there is some acceleration going on. So F net equals ma is a good place to start. You look at what your net forces will be parallel to the plane, and that will be 2g sine theta minus the frictional force. The mass is 2, and acceleration is what we're trying to find, so that will be equal to 2a. From here, I would substitute in what I know. So I know sine theta is 3/5 from earlier on, and I know friction is going to be 0.2 r. Then I would pause because there's nothing else we can do there and go to resolving perpendicular to the plane. Now, once again, in the perpendicular direction, there is no acceleration. The block isn't moving up away from the plane. So you can say that up will equal down in terms of the forces. So in this case, we've got R equals 2g cos theta. From earlier, we know what cos theta is. It's 4/5. So therefore, R is going to be equal to 8/5 g. Once we know this, we can take the R value and sub it into here. So that will give us 6/5g from the 2g times the 3/5 minus 0.2 times 8/5 g equals 2a. You can then solve this for a. Turns out to be 11/25 g meters per second squared, or roughly 4.3 meters per second squared to two significant figures. Example 3. Two particles P of mass 4 kilograms and Q of mass 5 kilograms are connected by a light inextensible string. The string passes over a smooth pulley fixed at the top of a rough inclined plane. The coefficient of friction between the block and the plane is 0.2. The plane is inclined at an angle of theta to the horizontal, such that cos theta is 0.8. P lies at rest on the plane and Q hangs freely from the edge of the plane 2 meters above the ground with the string taut. The system is released from rest. Assuming Q hits the ground before P reaches the pulley, find the speed at which Q hits the ground. There's a lot of text here, so let's go back through and highlight the key points. So we've got two particles, P, which is 4 kilograms, Q, 5 kilograms. It's on a rough inclined plane, and we're given the coefficient of friction. We aren't given the angle, but we are given cos theta is 0.8, so we can use that in our calculations. We know that Q starts 2 meters above the ground, and we know that the system is released from rest. We want to find the speed at which Q hits the ground. Now, this sort of information is making me think of SUVAT, so I'm just going to make a note to myself that SUVAT is probably going to be involved, but we'll need to find the acceleration from the forces first. Otherwise, we won't have enough information to find the final velocity. At this point, I'd also make a note to myself about that coefficient of friction. So friction, again at its maximum, and this time 0.2 r. And then I would move to labeling the diagram. So starting with Q, mass 5 kilograms, so weight 5g. It's on a pulley system, so we're going to have tension. And we know that Q is going to accelerate towards the ground, so A there. For particle P, that also has a weight, 4g. This angle is theta, so this will be 4g cos theta, and this component 4g sine theta. P is also attached to the pulley system, so we'll have some tension this way. We know that P is moving up the plane, so acceleration going up, and we know that the plane is rough, so our frictional force is going to come down this way. Only other thing to put on is the normal reaction force for P here. Next thing I would do is deal with that theta fact. So we know that cos theta is 0.8. Fractions are more helpful here, so that's 4/5. Again, we're going to draw a right angle triangle, theta, right angle, opposite, adjacent hypotenuse. Cos theta is 4/5, so this will be 4, this will be 5. Again, using Pythagoras, this means that the opposite is 3. Therefore, sine theta is going to be 3/5. You can work out tan theta as well, but I probably wouldn't unless I needed it later on in the question. Okay, so now we're ready to resolve our forces. Because this is a pulley system and the particles are accelerating in different directions, you do need to consider the particles separately. I'm going to start with particle Q. I'm going to do F net equals ma, and I'm going to take the down direction to be positive so that it follows the direction of the acceleration. Net force for Q is going to be 5g minus t, and that will be equal to 5a. Can't do much more there for now, so I'd move on to particle P. For particle P, I'll resolve perpendicular to the plane first, because we have a bit more information in the perpendicular direction. So again, in the perpendicular direction, A is 0, so forces up or equal forces down, means we're going to have R equals 4g cos theta. We know cos theta, so 4g and then 4/5. Therefore, R is going to be equal to 16/5g. If we now resolve parallel to the plane for particle P, and we look at our net forces, following the direction of acceleration, that will be t, and then minus 4g sine theta minus the frictional force. And that will be equal to 4a. Acceleration is the variable we want to find, so let's see if we can sub in some values for the other ones. For t, we can get t from this first equation by rearranging, so t will be equal to 5g minus 5a, and we can sub that in. And for friction, we know that that's 0.2 r, and we now know what r is. So if we put all of those pieces into this equation, let's see what we get. So we're going to have 5g minus 5a minus 4g sine theta, where sine theta is 3/5, minus 0.2 brackets 16/5g equal to 4a. Now just be really careful with your algebra here and take your time, but you can rearrange this to get 9a on one side and then 49/25g on this side. Means a is equal to 49/225g. Now we can finally use that a value in a SUVAT equation to solve the problem. So SUVAT, and for this I'm going to take down as the positive direction. We know particle Q is going to travel 2 meters down to the ground. We know it's released from rest. We want to find the final velocity, and we now know the acceleration is 49/225g. We do not know the time, but that's okay in this question. We then look for the SUVAT equation that does not involve t, and that's this one, and we sub in our values to find v. We then solve for v, and we get 2.9 meters per second to two significant figures. I've just taken the positive version of v there for the answer. Last example. A uniform ladder AB of mass 20 kilograms and length 5 meters is at rest with one end A on a rough horizontal ground and the other end B against a smooth vertical wall. The coefficient of friction between the ladder and the ground is 0.4. The ladder makes an angle theta with the ground. Given that the ladder is on the point of slipping, find the magnitude of the frictional force of the ground on the ladder. I'll go through and highlight some key points. So it's a uniform ladder, mass 20 kilograms, length 5 meters. It's a rough horizontal ground, but a smooth vertical wall. And we know the coefficient of friction between the ladder and the ground, 0.4. It says that the ladder is on the point of slipping. So again, that's limiting equilibrium. So our friction will be at its maximum, mu r. We're told the coefficient of friction, so let's make a note. That's going to be 0.4 r in this case. Now we can label the forces. So because it's a uniform ladder, its mass is going to act at the center, and that will be 20g for the weight. This component here will be 20g cos theta, because this is theta. And in terms of its position, because it's uniform, that will be 2.5 meters on either side. we've got a normal reaction force at B, which is going to be perpendicular to the wall. And I'm going to label that as RB because there is another one down here for A. So we can label that as RA. For friction, if you think about it, if there was no friction, the ladder would slip on the ground. Therefore, the friction is going to be acting in this direction to prevent that from happening. Now, with ladders questions, we're probably going to end up using moments, so we do want to know the perpendicular components of all the forces in relation to the ladder. We've already got that for the 20g cos theta, but let's think about that for the RB force. So that would be this direction. Now, if this angle at the bottom is theta, that means this angle here will also be theta. And that's because of alternate angles being equal. So if you look in here, we've got alternate angles happening. Therefore, this component of RB is going to be RB sine theta because it's not the component that's touching theta. Now I think we're ready to tackle the question. So for part A, we want the magnitude of the frictional force of the ground on the ladder. So for this part, because we're in limiting equilibrium, the forces will be balanced. So we can say that up equals down in terms of the forces, and also left equals right. So all the forces that we have going directly up are RA, and all the forces going directly down, it's just 20g. So that's it for that one. Going directly to the left, we have RB, and going directly to the right is friction. Now, because friction is happening on the ground, we also know then that friction will be 0.4 and then RA, because that's the reaction force on the ground. So if we just sub in 20g for RA, we can get that friction is going to be equal to 8g newtons. And that's it for part A. For part B, they want us to find the value of theta. So for this, we're actually going to take moments about A. Now I'm choosing point A so that I can ignore any forces at that point and just work with the other ones. It's in equilibrium, so clockwise will be equal to anti-clockwise. Clockwise moments, we're going to have 20g cos theta times 2.5, because 20g cos theta is the perpendicular component. Anti-clockwise, we're going to have RB sine theta times 5. Now we know from earlier on that RB is in fact equal to friction, which we now know is 8g. So we can sub that in there and also tidy up as we go along. That will give us 50g cos theta equals 40g sine theta. You can cancel the g's on both sides, and then you can rearrange for tan theta, and you'll get 5 over 4. That can then be solved to find theta, and you get 51.3 degrees to 1 decimal place. And that's it. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.